Any general questions, problems, anything? On the list of announcements, really just the one thing, which at this point is the project. Since hopefully Sprint 3 wrapped up yesterday, although you can still submit today. And so again, please look at it before the day it's due. It is quite possible it will take 8 to 10 pages to fully describe the kinetics of this reaction. So it is not likely something you can write up in an hour on the day it's due. And I did send out an email yet about my evening office hours for those who can't make the day ones. So check your email if you want to see those, or the Zooms are all under Zoom on my courses if you want the times. Any questions on that? At long last, we get to salts. We've actually been toying with salts off and on throughout this whole acid-base thing for a very good reason, which is that the salts themselves are, in fact, acids and bases. And, you know, a lot of the misconceptions around acids and bases that I keep railing against in high school really come out in this particular area, right? You know, it is frequently sort of advertised that bases are these things that have hydroxides, right? And that acids are these things that have H pluses. That's kind of sort of true for the acids. It's really not true of the bases, right? Although it is true of everything that the acids have H pluses and the bases have OH minus when I'm in water, right? I mean, we saw, due to good old KW, the autoionization of water, right? Water itself is always a source of hydroniums and hydroxides, right? Water is itself both an acid and a base. And so if I throw other stuff in water, because of all that other acid-base chemistry that's going on in there, specifically Ka, Kb, and Kw, even if the acid or base I added is not itself a source of H pluses or is not itself a source of hydroxides, there are things that will create hydronium or H plus, right, or hydroxide if they're in water, right? And so this idea of aqueous acids and bases is a little different than just an acid and a base if it were by itself without the water, right? And all of this really comes out in this salt issue, right? And of course, I had about, I don't know, a dozen emails about this and several people in office hours, right? The first thing you do when you've got a salt dissolved in water, dissociate it, right? That is, I maintain, the biggest theme of this entire semester, because acids and bases aren't the last we'll see of salts, right? And the issue with salts dissociating is that they do, right? It's not something I'm trying to do necessarily. It's not even something I want to happen necessarily, but if I dissolve a salt in water, it dissociates, which means my salts in water aren't salts in water. It's a cation and an anion in water. So if I throw a salt, say ammonium acetate, in water, I don't really have any ammonium acetate. What I have is ammonium and acetate, right? And I specifically pick ammonium acetate here, even though for a reason you'll see in a minute, it's probably the worst possible choice of salt, right? Is because the pieces, the cation and the anion from the ammonium acetate, are old friends of ours. We've seen ammonium before. Where? It's the conjugate acid of ammonia. And we've seen acetate before. It's the conjugate base of acetic acid, right? And so when ammonium acetate dissolves in water, it dissociates, right? But the two pieces I have are our old friends, a conjugate acid and a conjugate base. But as I often say, I hate that C word, right? An acid's an acid and the base is a base. Ammonium acetate, the salt, is actually an acid and a base. Bundled together when it's a solid as a salt, but in water, I have now released again my acidic species and my basic species because the ammonium is separate from the acetate, right? This is where, you know, at one point I promised never to do this again, but this is where you get that old high school lie, right, about salts and water. Because if you take any old acid and any old base, you're going to get a proton transfer, which gives you the conjugate acid and the conjugate base. If you bundle them together, you've got a salt, right? Technically speaking, ammonium acetate could be somewhat artificially looked at, right, as the product of the reaction of ammonia with acetic acid, right? Because again, like any old acid and base, right, the only thing that happens is the proton goes from the acid to the base. That gives me ammonium acetate. Now, again, one of the reasons I hate the simplifications here, right, is the tendency to somewhat fictionalize what happened, right? My bottom reaction there is more accurate, right? Ammonia accepts a proton from acetic acid, and I have separately ammonium, the conjugate acid of ammonia, and acetate, the conjugate base of acetic acid, right? On the other hand, right, it is common, even though I hate it, for people to actually bundle them, right? And that's why, you know, I keep calling it a high school lie or a simple oversimplification. It's not really completely false. It's just a little synthetic because my ammonium acetate does not exist as a compound in water because dissolved salts dissociate. The only time I would actually see a salt, an actual neutral salt molecule, is if my product were an insoluble salt, right? Because then it would precipitate as a solid and it would in fact be a salt, right? But for most of my acid-base reactions, right, where I get a soluble salt essentially as a product, two soluble ions, right? I really don't create a salt, I create two ions, a conjugate acid and a conjugate base, right? Even for ammonium acetate, it is common to write ammonia as ammonium hydroxide. Why? Again, because they want to keep throwing the hydroxide into the base, right? Ammonium hydroxide is just ammonia mixed with water, right? As we've seen, that is what happens, right? Because that is, again, essentially my KB reaction for ammonia, right? Although, again, I would argue that it is more rigorously scientifically correct to view the ammonium and the hydroxide as separate dissolved ions rather than as a single compound ammonium hydroxide. Right. But if I were to bundle the ammonium with the hydroxide, if I say ammonium hydroxide, what I'm really writing is ammonia plus water, right? And if I do that, even for good old ammonia plus acetic acid, I seem to get that old high school oversimplification that, hey, look, random acid, random base, I got ammonium acetate and water. Right. But again, I would argue that that misleads people more than it helps people. The only thing that really happened in any of my acid-base reactions is that if I add an acid to a base, a proton goes from the acid to the base, and I get what I get, which is usually ions. Right? In this case, I'm less worried about my forward reaction and more worried, not worried, but more interested in the conjugates. Right? Ammonium is the conjugate acid of ammonia. Acetate is the conjugate base of acetic acid. But again, drop the conjugate. Ammonium is an acid, acetate is a base. And so when I threw my ammonium acetate in water and it dissociated because it does, I got an acid and I got a base. And so my salt really isn't a separate category. Right? I mean, my cheat sheet has always been for, what kind of compound is it, acid, base, or salt? Right? And the salt is sort of a separate category only because it's an acid and a base. Right? But whether it's a pure acid, a pure base, or a salt, it has acid-base considerations, right, if I start mixing it with other things. Right? And so, as I said, ammonium acetate is probably the worst possible example of this, mostly because ammonium and acetate have roughly the same K. Right. And in the end, ammonium acetate is a relatively neutral salt with a pH of about 7. Right. For other salts, that's not so true. Right. What is true is that every possible salt you could write is technically the combination of an acid and a base. Specifically, the cation is the conjugate acid of something, and the anion is the conjugate base of something. Right. And conjugate or not, an acid is an acid, a base is a base. In most cases, not ammonium acetate, as you'll see on the next slide, in most cases, one of the species will be dominant because they will not have equal Ks. Right. Ammonium acetate is kind of special, right? They have very, very similar Ks because acetic acid and ammonia have very, very similar Ks, right? And so if I threw ammonium in water by itself, with a true spectator ion, right, the ammonium reacts with water in what is a classic Ka reaction, which regenerates my ammonia and gives me hydronium. The Ka of that is, of course, the Ka of a conjugate, so Kw over Kb, or 5.6 times 10 to the minus 10, right? Acetate by itself, right, again, is just a base that can react with water as the acid. Right. And that gives me acetic acid back and some hydroxide. That, again, is a classic conjugate. And so the Kb of that can be calculated from the Ka of acetic acid, which just happens to two significant figures to be the same as the K of ammonia. And so these reactions end up with similar Ks. Right. And so, again, it's the worst possible case of a salt because there's no dominant species. Right. It's worth pointing out, of course, there's really, since I'm all about listing all possible acid-base reactions, right, you could ask, why doesn't this happen? And the point of fact is it kind of sort of could, except again, right, this is the reverse of this. And what's the K of this reaction? It's K neutralization. And specifically in this case, if I've got ammonia and acetic acid, right, it's 10 to the minus fifth times 10 to the minus fifth over KW, which is 10 to the fourth. It's a borderline frickin' big number. And so the reverse reaction, right, has a really, really tiny, relatively speaking, K. So, right, I tend to be dominated by these two reactions. For other reactions, it's even worse, where, you know, if this is super freaking big, the K for essentially the self-neutralization of the salt approaches zero. Right? And so, you know, the basic gist of this for all possible salts, right, is that every salt is essentially an acid and a base. Specifically, it's a conjugate acid and a base. And so I can calculate the K from the K of the parent species, right? But in the end, there's an acid and there's a base, which means worst case scenario, there's two ice charts to solve. Best case scenario, there's not, right? And this is where, you know, I kept saying, well, let's ignore the chloride or let's ignore the sodium. Here's why I can ignore the sodium or ignore the chloride. If you take a salt like ammonium chloride, which is a little better behaved than my friend ammonium acetate, right? It's the same basic issue. Ammonium chloride is a salt. If it's dissolved in water, the first thing you do with the salt dissolved in water is dissociate it, which in this case gives me ammonium, which we were just looking at, and chloride, right? So ammonium, still the conjugate acid of ammonia, right? Chloride, on the other hand, is the conjugate base of HCl, right? How do I know? Put the proton back on, right? Well, HCl is a strong acid, right? And so, unlike in my previous example, where I had roughly equal Ks and Kbs for the two pieces of the salt, right? If I have a strong acid that has a near infinite Ka, the Kb of the conjugate is approaching zero. Right? And of course, a K of zero essentially means you form no products, right? Because after all, my K is always products over reactants. The only way I'm getting to zero is to have a really small numerator relative to a really large denominator. Right? And so even though technically chloride is a base, right? It's a horrible base. And even if there's a better acid than water in there, right, since the Kb of chloride approaches zero, no matter what acid you react it with, you end up with a K neutralization of zero. Right. This is why chloride is a classic spectator. Right. The same thing happens with nitrate. You know, I was talking before about how if you were paying attention in lab, you see a lot of nitrate salts, right? And there's two main pieces at this point as to why you see nitrates or chlorides, but usually nitrates, right? And why you see sodium and potassium salts, which we'll get to in a second. And the reason is partly solubility, right? Nitrates are really soluble. Chlorides less so, which is why even though it's a classic spectator, you see more nitrates than chlorides, right? but it's also the conjugate base of a strong acid. Nitric acid is, again, one of my strong acids, which means nitrate is effectively an infinitely weak base, or if you prefer, not a base at all. Right? And that's what you want in a spectator. You want something that's not going to interfere with the chemistry you're trying to do. If I throw a salt in my water, right, where both pieces, like ammonium acetate, have acid-base properties, both pieces potentially interfere with it, with whatever other acid-base chemistry I'm trying to do, because I've introduced an acid and a base that is capable of acting as an acid and a base. On the other hand, if I throw a nitrate salt in there, the nitrate can't do any acid-base chemistry of itself, right? The chloride can't do any acid-base chemistry by itself. And so it becomes a nicely behaved spectator, which doesn't get in the way of the thing I'm trying to do, which is why I can ignore it, right? Technically, if I'm making my list of acids and bases, as we were doing on Monday and last week, chloride does go under bases, right? But it is effectively an infinitely weak base and therefore doesn't do anything. And the same but reverse happens with sodium, right? For a similar reason, right? If I take something like sodium acetate, again, it's still a salt. If I dissolve in water, the first thing that happens is it dissociates, right? And so I get sodium ions and acetate ions. Again, there's my old friend acetate, right? No need to say anything about that. There's sodium, which at long last, those of you who kept saying, why do you keep saying sodium is an acid, it has no proton? Kudos for noticing that. And it's true, sodium ion by itself is not at all an acid because it doesn't have a proton, but I don't have sodium ion by itself, I have sodium ion in water. Right, and what sodium ion actually is, and there's really no good way to write this that doesn't look a little weird, but sodium is actually the conjugate acid of thus hydroxide, specifically sodium hydroxide. All right. And so in theory, and again, there's no good way to write this, right? If I have sodium ion in water, in theory, right, it can act as an acid with water as the base to remake the sodium hydroxide, right? If it does that, if it does that, it essentially frees up a proton from the water. Now, sodium is not the best example of this, right? Because sodium is the conjugate of sodium hydroxide, which is strong. So once again, you know, the Kb of this is approximately infinite because it's a strong base, which means the Ka of sodium, right, 10 to the minus 14 over infinity is, you know, essentially 0, right? So much like chloride and nitrate that we were just talking about, right, sodium as a cation is a classic spectator because it is an infinitely weak acid, right? The only reason I even bring this up is this doesn't have to be the case, right? If I have something like iron acetate, right, which again, in water, dissociates, right? Again, there's my old friend acetate. iron 2 plus is the conjugate acid to iron 2 hydroxide, which is not a strong base, right? And so metal cations, even though they technically don't have H pluses themselves, because they're conjugates of the hydroxide in water, right, they can actually essentially borrow, steal, release, whatever term you'd like to use, an H plus from the water. And so even a bare metal ion as a cation is technically the conjugate acid of something. If nothing else, the hydroxide that goes with it. All right. Yes, no, maybe. Right. In general, again, if I choose my salts carefully, I don't have to deal with half the salt, right? And this is part of the reason why I always say that 99.9% of the time, if you've got a salt in lab, dissociate it. But the reason why is because 99.9% of the time, only half of that salt is there for a reason, right? And 99.9% of the time, if it's a sodium salt like this one, it's the acetate you care about. I mean, I'm not saying that there's never a reason why you might want sodium ions, right? But a lot of my reaction types, this isn't the last one, the next two we talk about, KSPs and redox reactions, sodium is also a classic spectator, right? Sodium's inertness, sodium ions, inertness, right, is the reason why it's a classic spectator and the reason why I use it as my preferred salt. It's soluble. They tend to be cheap, which of course also has some merit. But, right, first and foremost, they're soluble. If you're going to do aqueous chemistry, you got to dissolve it. But it is also acid-base, I hate to use the word neutral, inactive, right? Because it's the conjugate of a strong base. It is also, as you'll see in the next couple of weeks, it is also KSP inert and redox inert, which means the sodium just stays the hell out of the way. Right. And so it is in my best interest, and if you don't care about mine, it is in your best interest to dissociate the salt so you can ignore the thing that's not doing anything. Otherwise, there's this constant problem of trying to figure out how to squeeze sodium into the balanced equation, when in fact, first of all, the sodium isn't attached to the acetate anyway, but it's also not doing anything, so there's no need to include it in the chemical reaction. Right? Your life becomes much simpler if you just take the spectators, put them in a corner, and ignore them. Right. Right. And so if I do that, right, I recognize that sodium is the conjugate of sodium hydroxide and therefore has no acid-base chemistry to worry about. I throw it in a corner and I'm left with only the acetate to worry about. Right. And the acetate is not a great base, right? This is a pretty small KB, but it is a base. Right. And so even if I don't have another acid or base in there, right, which we did with the buffers after all, right? I mean, we made buffers by mixing sodium acetate with acetic acid, right? Even if I just start with sodium acetate, my solution will have a non-neutral pH because, again, conjugate or not, a base is a base and an acid is an acid. All right. And so, you know, if you'd like to calculate it, right, it's the usual question. right? What is the pH, right? In this case of a 0.1 molar sodium acetate solution. And again, this is where I go back to the first question should always be, what kind of compound is it, right? Because that's going to tell you what to do with it, right? And if it's a pH question, you can be pretty sure the answer is acid, base, or salt, right? In this case, I won't even play that game with you, right? Since we just discussed that sodium acetate is a salt. And again, a salt dissolved in water, first thing I do always, dissociate it with it. Now, if it's the only thing I have, right, I now have an acid and a base, and I also have water as an acid and a base. I really just have to decide which pieces matter. So, you know, I didn't really do it this way because we just sort of did it before. But essentially, when I dissociate my salt, I put the cation on the acid side, I put the anion on the base side. Now, if there were something else there, I would also include those. But in this case, there's just water, right? Technically, again, there's 4 reactions. But again, if I recognize this is infinitely weak, I only have 2 reactions, acetate with water and water with water. And it's just biggest K first, which is pretty much never water and water, right? And so the only possible acid-base reaction I have here, or at least the preeminent acid-base reaction I have here, is the Kb of acetate in water, right? And at that point, it's just like every other equilibrium problem. I'm going to keep saying it because it's true. All equilibrium problems have 3 parts. It's the same basic issue. Balanced equation, K equation, build your ice chart and solve, right? So there's my K equation, right? There's my ice chart. I have an initial concentration of acetate from my dissociated sodium acetate. The stoichiometry is 1 to 1 to 1 as always. So my change line is, as always, minus x plus x and plus x. I plus C is always E, right? And then I take my equilibrium line and plug it in my K equation to solve for x. I've been slightly heartbroken all week, by the way, at everyone's resistance to constructing ice charts. I shouldn't say everyone's, but people who've emailed me or come to office hours. In the afternoon class, I actually had somebody who was resisting for 20 minutes making an ice chart, even though I begged him. And he was ROTC, so he kept calling me sir, you know, and he was all being polite about it, but he was frustrating the hell out of me. I'm like, come on, just make the ice chart, right? But he kept trying to look for a way to use Henderson-Hasselbeck without making the ice chart. And I maintain, right, even if you could use Henderson-Hasselbeck, which you can't here, right, it becomes clearer if you make the ice chart, because the signature for Henderson-Hasselbeck is that you have 2 initial amounts of the conjugates, right? And so you can train yourself to see Henderson-Hasselbeck in the ice chart. And again, if nothing else, as was the case with the sprint synthesis homework, right, I asked multiple questions that were not pH related because we're actually a good week and a half ahead in lecture of where we are in the syntheses. Right, the answer is somewhere in the ice chart, right? And so please, 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 at least consider making an ice chart or 2. All right. So if I plug my E line into my K equation, of course, how am I going to solve that? I always try. Again, you could Wolfram alpha. You could cross multiply, collect the terms, turn into a quadratic. You could stick it in your graphing calculator. In this case, the assumption works quite well. So it's pretty straightforward to solve it without a lot of algebra. Right, if I assume x is less than 0.1, the x in the denominator should be insignificant. I cross multiply and take the square root. Again, my test is always the 5% rule, which in this case, of course, is 0.005 as my standard of small. I'm 1,000 times smaller than that. So quite a good assumption. Right? If I put that back into my ice chart, which again should always be my last step in solving one of these, because again, as I'm fond of saying, right, X isn't necessarily the answer, but the answer is definitely somewhere in the ice chart. All right. In this case, the X is almost the answer. It asks about pH, right? Since this is a base, of course, I don't directly make any hydronium. In fact, I get the hydronium from Kw, the second acid-base reaction that I have here. All right. But I can do it the shorthand way. All right. My POH is the negative log of the hydroxide concentration. And as long as I'm at room temperature, the pH plus the POH should be 14. All right. And I end up with a pH of almost 9. Right. And so, again, I started with a salt, not a classic acid or base. Right. But I end up with a reasonably basic solution. And in fact, my next example will be even more basic. Right. And so my salts can be corrosive in the old acid-base way, right? Even though they're not classically acids or bases, right? They are, in fact, conjugate acids or bases. Yes, no, maybe. Right. Here's a different salt, similar question. The pH of a solution of 0.0707 molar potassium phosphate. All right. Again, it's asking about pH. If nothing else, that's sort of a wink, wink, nudge, nudge that it's an equilibrium problem, because in most cases, right, pH is coming from a weak acid or base equilibrium. So, like all equilibrium problems, 3 parts, right? First and foremost of which is, right, the balanced equation. Of course, it's a little less obvious, perhaps right off the bat with my salt, because I have to do some prep work with the salt in terms of, first of all, dissociating it, because salts dissolved in water do dissociate, right? And then I have to decide what to do with the pieces, right? In point of fact, I would argue you can do what, I did a minute ago, which is, acid base. Since it's just a salt, maybe this doesn't really do anything for me, because the salt gives me one acid and one base. I haven't added anything else to it. And of course, I just have water, right? Technically, that means there's 3 reactions, because I maintain that, right, reacting the potassium with the phosphate is never going to yield me much of anything, right, since I just dissociated it, right? But again, right, the issue is over the pieces. So here's good old potassium, right? One of my naked metal ions. It is the conjugate of potassium hydroxide, which is strong. So again, like sodium, the Ka of this is going to be approximately 0. All right. And so potassium is the other classic cation spectator, right? Whenever you don't have a sodium salt in lab, you probably have a potassium salt for the same, essentially 4 reasons, or 5 if you count price, right? They're soluble, right? They are acid-base spectators, and as you'll see shortly, they're KSP spectators and redox spectators. By shortly, I mean a week or so, not today. Phosphate's perhaps a little more complicated. Although we have seen phosphate before, phosphate is actually the third conjugate base of one of our polyprotics, phosphoric acid. Right? And I mean, I was going to do it later, but we could do it now. I mean, this is a general strategy. If you want to know what the conjugate is, right, if you have a proton, take it off. If you don't have a proton like sodium or potassium, put a hydroxide on, right, for the bases. For the acids, which are, or excuse me, for the conjugate base of the acids, I'm just going to add as many protons as it takes to get neutral, right? So if I've got an anion, in this case it's a 3-, I need to add 3 protons to get to a neutral molecule, right? That is essentially what I did, you know, with the acetate. It only is a -1, so it only needed 1 proton. The phosphate's a -3, so it needed 3 protons. Right. And so the good news is the potassium's a classic spectator, so I'm just going to ignore it like it's not there, because it's pretty much ignoring everything else like it's not there. Right. And my phosphate is technically a polyprotic base. Now, as you'll shortly see, the same thing happens in reverse to what happened when we did phosphoric acid the first time, right? The difference in the Ks is so significant that typically only the first dissociation matters, right? But if I have to, 3 ice charts, 3 balance equations, 3 K equations, 3 little algebra problems. Right. So I've got phosphate, right, reacting with water and what's a KB. That does create hydrogen phosphate, which is itself still a base, which could do a second reaction with water to give me dihydrogen phosphate, which is still a base, which could react with water to give me phosphoric acid back, right? So I have 3 KB reactions, each of which is the conjugate of the Ka of the polyprotic. So again, it's Kw over the Ka, right? And so, you know, I'm starting here. So, you know, this is the first reaction I do. This would be the second. This is the third. Again, note, there's still a big difference in the Ks. So I really don't expect the second one to much matter. But we'll find out. The other thing to note is the size of KB3, right? That's a reasonably large K value. Right. And so as you'll see, it gives me a reasonably basic solution. But, you know, I don't have to solve all 3 at once. If I have 3 equilibria, hopefully I can solve them as 3 separate, mostly separate equilibrium problems rather than as 3 simultaneous equations. And so each part, right, has 3 parts: balance equation, ice chart, K equation, and solve. Right. And so my initial concentration of potassium phosphate, right, there's only 1 phosphate per potassium phosphate. So the concentration of phosphate is the same as the concentration of potassium phosphate. The potassium concentration, of course, is 3 times larger if I cared. All right. The change line is still minus X plus X and plus X. I plus C is still E. And if I don't know anything else, which I don't, other than the K value, my pathway to solve for X is K. Right. Sadly, my assumption does not work here. But of course, I always try it. All right, so if I assume x is less than 0.0707, cross multiply, take the square root, I get 0.0349. It's less than 0.0707, but it's not much less. It's only half, not 1/20th. All right, so again, Wolfram alpha, graphing calculator, or good old quadratic. All right, so I cross multiply, collect all the terms on one side. That gives me my coefficients. I get a negative root, which makes no sense in my ice chart. The positive root that does make sense is 2.73 times 10 to the minus 2. All right. And of course, that goes back into my ice chart to finish it up. All right. X should always go back into the ice chart. All right. First and foremost, it might tell me if my X value makes any sense or not. All right. But again, somewhere in there is either my answer, or in this case, the starting conditions for my second equilibrium, because of course, my hydrogen phosphate is still the conjugate base. All right. And so, as I said, I don't expect this to matter. But the only way to know is to see if it does matter. All right. And so my initial conditions for the second equilibrium are, as always, based on the final conditions for the first equilibrium, because they follow each other consecutively, though not quite independently, since they have species in common. Stoichiometry is still -1 + 1 and +1, and I plus C is still E. All right. And so this is yet another case where I get triply good news. Right. If I plug that into my K equation, I, of course, am going to try my assumption. Right. More so than the previous time, I really, really care whether it works. Right. And in fact, it does. If I assume X is less than 0.0273, right, the 0.0273s cancel. X ends up being the KB, which is 10 to the minus 7. That is much smaller than 0.0273. Right. And so again, this counts as triply good news. One, it means no ugly algebra. Really, more importantly, even though you might hate ugly algebra, right? Even more importantly, it means I don't have to do the third equilibrium, right? If the second one doesn't matter, the third one's going to be even smaller. But again, almost most importantly, right, it justifies my approach, right? The fact that that one is insignificant, it means that little bit is not going to change the concentrations which satisfied the first equilibrium, right? I kind of sort of need that to happen whenever I have multiple equilibria in order to truly, truly, truly be able to treat them as separate reactions. Right. And so, right, these two species, all of a sudden my pen doesn't work. But, whoops. Right, the hydroxide and the hydrogen phosphate, right, effectively unchanged because the X was so small. Those are the two species that were in the first equilibrium. Right. If we needed the third, the only time you would ever really need the third is if you actually cared about the phosphoric acid concentration. It's not going to change the pH any because the hydroxide is not going to change. But the only phosphoric acid you have is actually from that third reaction. Right. And so, right, again, the hydroxide concentration was 2.73 times 10 to the minus 2. Right. either stick it in KW if you want to demonstrate that, in fact, it's yet another equilibrium to solve. Or, of course, there's always my shorthand approach to solving that equilibrium, which is calculate the POH and subtract it from 14. Right. And I end up with what is really a very basic solution. Right. I mean, 12.44 is pretty close to Drano. Right. Drano, most drain cleaners tend to be somewhere around pH 13 or so. Right. And so just because it's a salt doesn't mean it's not a reasonably good acid or base. And along those lines, it doesn't mean it's not particularly corrosive. Right. That's known. Maybe. Again, for the salts, it's the same procedure every time. First thing I'm doing always is dissociating them. Then I'm looking at the pieces. They're conjugates. So to evaluate their Ks, I need to know what they're the conjugate of. Right. And the cation is the more complicated one. Right. If it has a proton like ammonium, take it off. That'll tell you what the conjugate is. If it's a bare metal ion with no proton, just add as many hydroxide as it takes to be neutral. All right. For the anion, it's always just a question of H pluses. Add as many H pluses as it takes to become neutral. All right. And the key step, at least in terms of simplifying things, right? If you look up the Kas and the Kbs of the parent, not the thing you have, but the thing it's the conjugate of, if any of them are strong, you got a spectator so you can ignore it. All right. And that's why I say ideally, if you're choosing your salts carefully, you've always got a spectator, right? Because it keeps your solution chemistry clean. You don't want to be throwing things in that are going to be doing side reactions and getting in the way, right? Hence, nitrates and chlorides for anions as spectators and sodium and potassium ions quite frequently as cation spectators because they conveniently stay out of the way. Questions or problems with that? Whoops. So we'll do some practice problems on Friday. Happy St. Patrick's Day if you're celebrating. Friday is, of course, St. Joseph's Day. We should all celebrate that.